Welcome to our AP Chemistry notes on hydrides and oxides. We're kind of taking a pause. We are most certainly going to be talking about acids and bases in the near future. But there's some random topics that, at least they're going to seem random for a while, that connect with acids and bases. And the elements hydrogen and oxygen are most certainly one of those. These are two very important elements in all of our chemistry work, and so it's good to take a day and just look at what makes them unique and how we can do some predicting based on knowing their chemical possibilities. So speaking of hydrides, most metals react with an acid to produce hydrogen gas. That's like kind of one of our definitions of a metal is it will react with a metal. One of our definitions of an acid is that it's going to react with metal to produce hydrogen gas. And we did this. You'll recall we had some hydrochloric acid and we dropped some nuggets of zinc into it and it made hydrogen gas, which we collected in an upside down test tube. And then we tipped that over and stuck a flaming splint in real fast and it would ignite the hydrogen and make a whoosh sound. So this is actually how it's thought Henry Cavendish first discovered hydrogen. He's at least the one we give credit for hydrogen to. We certainly can make hydrogen from the electrolysis of water. That, of course, involves electricity. That is a redox reaction like we studied back in electrochemistry. It's not convenient to do it that way, but it can be done that way. The problem is, of course, you're burning coal to split water into hydrogen and oxygen by electricity, and then you're going to use that hydrogen to fuel your car in the hydrogen fuel cell in order to not burn hydrocarbons. Well, if you remember, I just said we started by burning coal. So it really, to get away from fossil fuels in our cars with hydrogen cells, we would need another way to get the electricity for the electrolysis of water, or we would need another way, period, of forming hydrogen. We can also have the reaction of hot carbon or methane with water. That would evolve hydrogen gas as well. There are many ways, and this, of course, is a big deal as we start looking at alternative fuels. We're not going to go there with this class. Okay. What I do want to point out is that hydrogen has the potential of being a +1 or a -1. And you should remember that from pre-AP. So when we react it with a metal, that is any element in like 1A through 5A, it's going to become the anion. It's going to be the hydride because metals have to lose electrons. So if hydrogen's around there, it's going to gain the electron. And so we have hydrides that way. When it's with a non-metal, it's those nonmetals with their high electronegativity that are going to take the electron, and so now hydrogen is going to be its positive form and be the cation. And so I've built this little chart just so you can kind of see how this works out. Notice how you get this split here between hydrogen being hydride and hydrogen being in the front. And so you can kind of get the idea of these common compounds. No big deal. We studied this in pre-AP. You have your positive metal and then your negative hydrogen. And over here we have our must be negative non-metal, so we would have a positive hydrogen. Okay. There are a couple exceptions to our patterns, as you'll notice here, but really no big deal. Not something that this chart is not worth memorizing for the test. Don't do it. It's not worth it. I just wanted to demonstrate to you how it really splits between metals with hydrogen and non-metals with hydrogen. And even check, I say that in general, check out that we have some non-metals, or at least ones that we call non-metals, that also tend to be positive and therefore makes hydrogen the negative. Okay, so with that said, here is what is important for AP chemistry. Our ionic hydrides, that is, when we have a metal with hydrogen, we consider them to be basic. And you'll remember our definition of a base is something containing hydroxide ion, and that's a good definition, but check out what happens. Even though I have no hydroxide in calcium hydride, if I were to add water to it, it would form calcium hydroxide and hydrogen gas in the process. Okay, so it's going to form a base. Now let me pose this question to you. I have a beaker, and I fill it with calcium hydride. What's in the air above the beaker? Well, all air has a little bit of water in it at least, and so that will react. So eventually over time, my beaker is going to start reacting, and if I leave it long enough, instead of having a beaker full of calcium hydride, I would have a beaker full of calcium hydroxide. So, I mean, I could actually ask you to, given a bit more data, to calculate how long that would take. It'd be a good kinetics question. But with that said, what I want to point out is how check this out, it's going to be a reaction between calcium and hydroxide, forming calcium hydroxide, and hydrogen with hydrogen forming hydrogen. So it very much is a swapping of parts, if you will. It's very similar to a double replacement reaction. So it's really not a new reaction. I just wanted to be sure to point this out, that it really works like a double replacement reaction there. Okay. Now let's talk about oxygen. Oxygen is very reactive, and so it will form compounds with almost every element, except of course the noble gases, and it doesn't form compounds with gold, palladium, and platinum, which tends to be why we use those for jewelry, because it will never oxidize, it will never rust. Even silver, if you're not wearing it over time, it will oxidize and turn brown. It actually is not oxidizing with oxygen in that case, but that's not anything you need to know. So it turns like, that brownish, blackish, tarnish color. Anyway, these never tarnish, meaning they would never form with oxygen. So almost all elements will oxidize. Now that is the general term. When it happens to iron, we specifically call it rust. It is thought that Carl Scheele first discovered oxygen. He decomposed mercury oxide into a gas and discovered that the gas was oxygen. Although he was not the first, as far as we know, to publish, or at least the first to publish his findings mainstream was Joseph Priestley. But he did not call it oxygen. He called it dephlogisticated air because it helped things to burn well. And so phlogiston is garbage. And so not many people took them seriously because phlogiston, even at that time, still had issues already that people weren't figuring out. It got its name from Lavoisier, who probably knew about the work of Scheele and Priestley and redid all the experiments in his own lab because, of course, only he could do them the right way to be sure you get the right results. But when he did that, he named it after the French words for acid former. Now, if you'll think about why would we call oxygen acid former, well, how many oxyacids do we have? Oh yeah, we have a lot of oxyacids. There's only a few non-oxyacid acids out there. Okay, so oxygen combines with a lot of elements. When it combines with the alkali metals, I just want to point this out. This is nothing to memorize, although you should be able to do this because we've talked about assigning oxidation numbers. We have our normal oxides, like potassium oxide, where oxygen's a -2. But we do also have our peroxides, like potassium peroxide or hydrogen peroxide, where the whole O2 has a -2 charge, meaning that each oxygen is a -1. And then we can actually, some of the elements will form what's called a superoxide, like this. Now check this out. If potassium is a +1, then both oxygens together must be a -1, which means each oxygen by itself is a half. Well, that should be interesting. You're like, well, how do we get half an electron? That doesn't exist. Well, it doesn't, because oxidation numbers don't exist. That's something we as chemists have made up to just be able to assign numbers to elements to be able to compare. So again, it's not something you need to memorize. Here is, a table of oxides, peroxides, superoxides. Okay, not worth memorizing. But what I absolutely don't want is for you to be working on the test and be like, oh, well, cesium with 2 oxygens does not exist. This is a trick question. I'm not going to answer it, because that's a foolish way to take the test. So if they tell you CSO2, just go with the fact, pretend it exists, because it probably does, and answer their question anyway. So now you've seen it. Now at least it won't be, you won't be like, oh, it's a trick question. Okay, I'll point out that group 2A metals do not readily form peroxides. You can see some of them are missing. And it would take a lot of oxygen to make those happen. You have to have tons and tons and tons of excess oxygen going on there. Okay, the underlined one being their more likely form. So it's really just those super reactive alkali metals that would form a superoxide or a peroxide. Typically we don't get more than just a normal oxide forming unless we have tons and tons and tons and tons of oxygen around. Yep. So speaking of having oxygen around, we have those metals in the middle of the table, like the transition metals and the ones underneath the stair-step line that can have multiple oxidation states, which means if they're working with oxygen, they can actually form more than one kind of compound with oxygen. So we already discussed the point of limiting in excess reagents, but I want to point this out again. It's just simply worth repeating since we're talking about oxygen. We can have different compounds containing oxygen if the metal can have more than one charge. So for example, I take some copper and I burn it in limited oxygen, and I'm going to end up with a red oxide. Now check out how if oxygen's a -2 and I have 2 coppers, that makes each copper worth a -1. So copper's only being, a +1. Copper's only being a +1 in this case. But if I had excess oxygen, I'd get a black oxide, and that's going to be a +2. So you could actually tell, in this case, which oxide you ended up getting by the color. Now, if I were just to take some copper and burn it in the air in the room, chances are I'd actually get a mix of that. So I'd want to really be sure I limited the oxygen if I wanted only red, or really be sure I had tons of oxygen around if I only wanted the black. Okay, and this should make sense in that the more negative oxygen there is, the greater the positive value would be on the metal. So it's a good way to predict if, and this is a good general rule to have in your head, memorize, to have in your head, if there's more oxygen around, the metal will be its higher oxidation state. And if there's less oxygen around, the metal will be its lower oxidation state. And that's just a very good general rule to have in your head, because that is exactly the way it would always work out in terms of, figuring out from the oxygen what it is. Okay. So let's talk about reactions with oxygen. We talked about how metal hydrides can form a base. Well, here we also have that metal oxides will form a base. Okay, so I point out as we write water as HOH, this is a synthesis reaction, and we actually had these in pre-AP, and I've had you memorize from pre-AP that a metal oxide in water forms a base. Okay, now often what we'll do is we'll call this compound a basic anhydride, meaning it's lacking water. If not for that lack of water, it would be a base. The moment you take your sodium oxide and you add water to it, it's going to become sodium hydroxide base. So when I want sodium hydroxide, I could actually just call up a chemical company and say, hey, send me some sodium oxide, and I could just add it to water and make my own base. It would be totally doable. So again, we have discussed the type of reaction. I just wanted to introduce you to the vocabulary, basic anhydride. So previous, where we had, it was calcium hydride and water, and this isn't going to be balanced, but that's fine, forming calcium hydroxide and hydrogen gas. Okay, and you can go through and balance that if it needs it. When we had that situation going on, we could have called this also a basic anhydride, because for lacking water, it would be a base. And here, so a metal hydride is a basic anhydride. A metal oxide is also a basic anhydride. Okay. And then we have our nonmetals. Our nonmetals will combine with water to form an acid. And this is, again, a form I had you memorize in pre-AP. But it's, again, just a synthesis. Okay, so in this synthesis reaction, we would get an acid, and so we call them acid anhydrides. If adding water, I'm going to get an acid, an oxyacid specifically, but we would call that acidic anhydride. So I want to introduce that vocabulary to you. An acidic anhydride is one that, with the lacking of water, would otherwise be an acid. And I do make a little note, there's some that aren't soluble and won't combine with water. So I can't necessarily just make my acid by getting some B2O3 and throwing in water and waiting for the acid to form, because I'd be waiting there pretty much forever. So you would have to pick wisely how you go about making acids of those. Okay, now also metallic oxides and non-metallic oxides react with each other to form oxysalts. Now that really has nothing to do with our acetic anhydrides or basic anhydrides. I just want to throw that in because we're still talking about oxygen, and that's another reaction with oxygen. If I have a metal oxide and a non-metal oxide, I would get an oxysalt. And again, these three are straight off of the reaction rules I've had you memorize from pre-AP, and we worked again with at the very beginning of the year. I'm expecting you to be able to predict and balance these. I just wanted to throw in the vocabulary. So be aware of what we're trying to say with the vocabulary. If that's tripping you up, then please come get help to figure out what the vocabulary itself means. Speaking of oxygen, let's talk about combustion. Okay, and I really want to point this out. I've said this earlier when we did our reactions, but I want to make this point clear. Because recently in pre-AP, we've started discussing reaction rules, and the on-level teachers have been doing this big thing about combustion. And that's great, because they were telling their students, hey, combustion is taking a hydrocarbon and adding oxygen to it, and you will always get carbon dioxide and water. That would be fabulous until you get to the AP test, and you're like, a metal combusts in an atmosphere of oxygen. What are your products? And students want to say carbon dioxide and water. And I'm sitting there thinking, how do you transmutate, because that's the only way I can imagine of doing it. How do you transmutate magnesium to become carbon and hydrogen? That's some alchemy going on there. So please, as much as I know that the other teachers are saying hydrocarbon combustion, unfortunately, what students seem to pick up is the word combustion, and then think with combustion, those are the necessities, and that's not the case. Check out, this is combustion as well, okay? And still we get very different results. So please be very careful with the word combustion when you see it, when you read it. Know what they're combusting. It should make sense if you're combusting carbon and hydrogen, you get carbon dioxide and water. It should make sense if you're combusting magnesium, you get magnesium oxide. All right. So, I mean, obviously what you start with, you have to end with. This we have discussed, and this is definitely just a combination reaction straight out of pre-AP. An element and another element forming a compound. You should be able to do that without much thought involved at all. Okay. Now, what if there's not enough oxygen around? Because we could have a case where there's just not enough oxygen around. In that case, we would get incomplete combustion. I want to point out, and I did this earlier this year, but there you go. I want to point out the differences between complete and incomplete combustion, because there's a difference. With incomplete combustion, we get carbon monoxide and water, not carbon dioxide and water. And still, I'm talking the combustion of a hydrocarbon. If I had incomplete combustion of a metal, it would be very different. That's like back to the case where I had copper 1 oxide or copper 2 oxide, where I got the red form or the black form. That would be the difference in the incomplete combustion of a metal. This is incomplete combustion of a hydrocarbon. So we get carbon monoxide and water. And I really don't think they're going to try and trick you with that on the test. I don't think like they're going to try to sneak in the word incomplete and make it just, make you think it is complete and then it's supposed to be incomplete and you're wrong on everything. Very likely they would show you the equation to start with and then ask you to do calculations with it from there. But this is actually why we have catalytic converters in vehicles, because we really, both both carbon monoxide and carbon dioxide are poisonous to the environment. They're going to trap in heat. If you breathe it for a long time, you're going to suffocate because your body needs oxygen, not carbon dioxide or carbon monoxide. But comparing the two, carbon monoxide is much worse than carbon dioxide. So, because you'll notice we put up carbon monoxide detectors in our house, not carbon dioxide detectors. So it really is good just for everyone's general safety that we try to get rid of the incomplete combustion in your car, and that's what a catalytic converter would help us do, is even if we did get incomplete combustion, it will hold on to the carbon monoxide until we add some more oxygen to it to get that carbon to go up in oxidation number and become carbon dioxide. And again, did you catch that? With our metal, copper, we had a copper 1 oxide and we had a copper 2 oxide, and the more oxygen we had, the higher the oxidation state. Same thing going on with our carbon here. If I have a limited amount of oxygen, I'm going to get incomplete combustion. This is carbon being +2. When I had complete combustion, I had carbon dioxide. That's carbon being a +4. So still, the more oxygen you have around, that higher the oxidation number will be on the metal or the nonmetal that it's attaching to. That should make sense. If I have more of something around, I can spread it around more. So hopefully that makes sense in your head. Anyway, just some basics about oxygen and hydrogen. I know it kind of seems like random thoughts, but the idea is that oxygen and hydrogen are very important elements to our work, especially as we're about to get into acids and bases. You're going to see oxygen and hydrogen a lot when it comes to acids and bases. To that extent, your practice is going to be based on, can you figure out some basic anhydrides and acid anhydrides, or predict which one you're going to get. If you can do that, you're probably well set on this topic for the AP test. So good luck on your practice, and I'll see you next time.